let's go ahead and talk through this process. All right, so once again, either of the methods can work for this. You have a denominator factor of b, or in this case b squared, and a base a squared. So you only have the two different bases, so you can do this relatively efficiently in each way. But let's take a look at the first method, because again, that's what most students prefer. Right, so if we rewrite this numerator as a single fraction, what will our LCD be? We need a b squared and we need a squared. Okay? And so if we take our first fraction's numerator, we need to multiply it by the LCD factors missing from its denominator. What's missing? The a squared. So what's a squared times a squared? A to the fourth. Okay, minus b squared, our next fraction's numerator, times what LCD factor would be missing from this denominator? B squared. So b squared times b squared is b to the, also b to the fourth. Okay, so here's our single fraction in the numerator. Okay. In our denominator, when we combine these into a single fraction, again, we can find our LCD. We need a factor of b, and we need a factor of a. And so when we simplify, or combine the numerators, we take the numerator of the first fraction, a, times what LCD factor is missing from its denominator, and a, so a times a is a squared, plus our next fraction's numerator, b, times the missing LCD factor from its denominator, which is also b, so b times b is b squared. So here's our single fraction here. So we've converted this from the complex, or it still is a complex fraction, but now we converted it into a problem similar to what we did in 4.2, dividing fractions. So instead of dividing, we can multiply by the reciprocal. Well, in order to do that, we want to factor everything. Do you notice anything about this binomial? Okay, whenever you check it, are there common factors you can remove? No. Since it's a binomial, is it a perfect, is it the difference of squares or the difference of cubes? Are there two values that you can square to get a to the fourth? Yeah, it's what value squared? It's a squared squared minus b squared squared. So you do have the difference of squares here. So you want to think of this in terms of its factors. So this numerator factors into the sum of the terms and the difference of terms, the terms being a squared and b squared. So we take the sum times the difference. Okay, and then this denominator is going to stay just as it is. And now we can even go further and factor a squared minus b squared. So if we look at that, we wind up with a squared plus b squared times a squared minus b squared. Oops, I'm sorry. What does a squared minus b squared factor into? Again, it's the difference of squares, so it's the sum of the terms times the difference of terms, a plus b times a minus b, all over a squared b squared. And in the same process here, let's go ahead and convert this from division into multiplication by taking the reciprocal. So we move this factor ab into the numerator of a fraction, and the a squared plus b squared into the denominator. And now you can look to cancel your common factors. A squared plus b squared cancels. This b cancels with one of these b's. This a cancels with one of these a's. And so when you write your answer, your final answer is a plus b times a minus b all over ab. Now, were there any factors that were removed from the denominator that you have to account for domain restrictions on? The only thing that canceled was a squared plus b squared. Will that ever equal 0? It's only one case where it ever will, if both of them are 0. So we know that a and b can't be 0. Is that shown in our solution, simplified form? Yeah, so you don't need to put any restriction. That would be your answer. And if you left it as a squared minus b squared over ab, that's okay as well. All right, now let me show you an alternate method for solving this that, if you can see, may save you some time. And it is possible you're going to see something similar to this at some point. All right, if you look here, again, just and individually. Okay. Do you notice anything about the numerator? First of all the expressions of terms are pretty close, right, Alan? Yeah, the numerator itself is the difference of squares, right? Good. So if you look at that, you really have a over b quantity squared minus b over a quantity squared. So we can factor that into the sum and difference of those terms, the terms being a over b and b over a. And so you can factor this into the sum and difference of those. By doing this, what are we able to do as our second step here? We can cancel these entire factors. And now we just simplify our numerator up here. What's the LCD for these two terms? AB. We need a B and we need an A. We take our first fraction's numerator times the missing LCD factor from its denominator. It's missing an A. Minus our second fraction's numerator, B, times the missing LCD factor from its denominator. Okay. And so we get our answer. It's a little more efficient that way if you see it, but look for those. Anytime you see perfect squares, and whether it's in a common form or a more uncommon form like this one, it can simplify your work.